you've got a printer, but there's one big problem: the config file is missing. For that 3D printer model, there's no predefined Klipper configuration in the official repository. This is where 99% of people give up. Everyone thinks the missing file is a problem, but that's wrong. You need a detective's method to reverse engineer every crucial piece of information, and by the end of this video you won't just get Klipper working, you'll have the confidence to configure any unsupported 3D printer. Let's get started. Our first stop is always the Klipper config folder, and we start searching. Why? Because if your file is here, you win. We scroll down past the Neptune 2, past the Neptune 3, looking for my target, the Neptune X. But, like most unsupported machines, the Neptune X config file is missing. Therefore, since the simple copy-paste solution failed, we have to move on to phase 2, becoming hardware detectives. We have to carefully build our own configuration, piece by piece. Let's see how. This video is made possible thanks to PCBWay. PCBWay offers high-quality PCBs starting as low as $5 for 5 PCBs. Besides that, PCBWay also offers high-quality CNC machining, 3D printing services, sheet metal fabrication and more, which makes PCBWay your one-stop shop, no matter if you're a hobbyist or an established company. Alright, the first crucial piece of information we need to find is the identity of the main control board. So, I turn off the printer, unplug the power cord and open it. We are not just looking for a simple model name. These boards are often generic with custom firmware, and they might have a name like Robin Nano that isn't specific enough. Therefore, let's take extremely high-resolution pictures of every single chip, every connection and every tiny label. I always take these photos first because it makes identifying the MCU chip, the stepper drivers and all the peripheral pinouts much easier when we are back at the PC. Plus, it gives us a clear reference for when we have to put all the plugs back in later. Crucially, even if we find a generic board name and revision in Klipper's config folder, using it without verifying the pinout is dangerous. That's why we are gathering this data to build or verify the config safely from the ground up. We've got our high-res photos, but a simple Google search for the board name looks like a dead end. These boards are often custom variants. This is where the detective work really starts. Another popular 3D printer firmware is Marlin, so we hunt for the ultimate cheat sheet for information. To find the required missing pieces, let's look through the Marlin sources, starting with the boards.h. Luckily, we find the Neptune X here. With the board confirmed, we should find the pin definitions needed for the Klipper config in the pins folder. From there we then can look for the pins file with the exact MCU and pin definitions we need. Finding that file is the Klipper jackpot. Bingo! Here's the pins MKS Neptune X.h with all the required pin definitions for the steppers, sensors, fans and heaters. Before I show how to continue from here, let's assume that we weren't lucky finding that specific board or the printer wasn't based on Marlin.
Sorry.
We don't just need the MCU name, we need to know which version we have. Therefore, to stay on the safe side, we must execute a 3-part strategy. Getting the original firmware to have a failsafe to revert the 3D printer to stock condition is the first thing, so we can always go back. Second, we look for schematics online to trace the connections. Third, we could ask the manufacturer's support for schematics and the exact MCU version. If you don't find it, ask for it in the 3D printer related group on Facebook or Discord. Pro tip: if you don't know the correct parameters for your MCU to use, AI may help out. For the STM32XX I asked what are the most commonly used bootloader offsets used for the STM32F4XX boards. After a short moment I get the answer: bootloader offset 32 KB bootloader. As I found out later, that was wrong. Next we will try to trace the connections on the board visually and by using a continuity check. Unfortunately, a heatsink blocks the direct view on the stepper drivers. To get it off, I soften the thermal glue that holds it using a hot air gun at 130 degrees Celsius. Then I slide some dental floss under the heatsink and pull it gently through the softened glue. Finally, When the heatsink is off, I clean it with some IPA and scrub away the remaining glue, so I can see all the pins. For the other stepper drivers, I leave the heatsinks because they will be obviously wired identical. Now, the most crucial step in safely setting up an unsupported printer is building the configuration from scratch. This requires locating every pin on the MCU. This process is dangerous if done incorrectly, as a single wrong setting can damage hardware. That's why we rely on a careful measurement using a multimeter. As an additional safeguard, we take our high-res pictures which we took from the board and try to visually find the traces connecting the peripherals to get the pin numbers. I load it in GIMP where I can zoom in close. Overlaying snippets of the component pinouts from the datasheets helps too. Then I just draw colored lines following the traces from the stepper, enable, step and dear pins or the USB connection. Since not all traces can be clearly identified, checking the results and missing pins with a multimeter comes next. Set your multimeter to continuity mode. We begin by identifying the pins for the Endstops and the filament runout sensor and methodically work our way up to the motor and heater pins. These usually have components like pull-up resistors or debouncing circuits wired inline with the MCU's GPIO pins. Now the method is to start by probing the physical X endstop pin on the board connector. Then trace a connection to the nearest resistor or protection component. From the other side of that component, probe the MCU pins until you find continuity. As an example, for the X endstop, the continuity trace leads us to pin PA15. Write this down immediately. Next, we identify the pins for the stepper motor drivers, focusing on the three main signals. To clearly identify the pins to measure, I printed the pinout of the TMC2208 as reference. Then I start with the enable pin, looking where the trace goes and measure my way to the MCU pin. I write down the found pin. I repeat this for the direction and step pin and all the remaining drivers for the Y and Z axis and the extruder. Finding the thermistor pins took a little longer, but then I saw the larger caps with two resistors here, which, except of the cap size, look very similar to the debouncing circuits used for the Endstops. Only that these circuits will serve to smooth out the thermistor readings so that they don't jump around too much. Once confirmed, we can find the MCU pins for them, which I record for later too. Next, the fans and heater pins. These pins are PWM-capable pins connected to the gate of the MOSFETs that switch power for the hot end and heat bed and control the fan speeds. From the MOSFET datasheets, I know that the gate is the left pin. That's where we start measuring and working our way down over the protective resistors to the MCU pins connected to them. Again, write down the found pins. Accuracy here is vital to prevent runaway heating. Even if you aren't installing it immediately, now is the best time to identify the pins used for the Z-probe or BL touch, which usually requires two separate GPIO pins, one for the servo signal and one for the endstop signal. On my board are a few more connectors which I measure too, just in case I need that information. Once we have all the info, the MCU, the bootloader size and the correct pin assignments, we can use that data to configure the compilation for the klipper.bin using Kiau and finally flash it following the correct procedure for our control board. So I started Kiau, selected Advanced and there built. Watch my other video, Master Klipper Installation in Minutes with Kiau, Easy Guide for more on Kiau and Klipper setup. We find the compiled file in the Klipper out folder named klipper.bin. To flash it on the Illego Neptune X, I copy the file from the Raspberry Pi to my laptop using SCP and rename it to Illego bin. I reinstall the board into my 3D printer. For now, just connect the power and the display, but leave everything else unconnected. Then I turn on the printer. I see that the firmware is flashed and the screen says Update 100%. The klipper.bin is flashed. Connect the Raspberry Pi on which we installed Klipper and mainsail or Fluid to the USB port and restart Klipper. But the printer is still not working. You just gave your printer a blank brain. Now we have to build the printer.cfg file from scratch, step by step. We start with a bare minimum config to confirm we have communication. We add only the MCU section for connection and the printer section to load Klipper's basic framework. To find the correct device, run lsusb without the printer connected to the Klipper host, then connect the printer and repeat the command. The USB device that appears is the one we have to provide in the MCU section. We hit firmware restart. On success, the console must connect and say Klipper is ready. But if it fails with unable to connect, we must check the serial ID and the flashing process before we can move on. Since restoring the original firmware brought the printer back to life, I knew that the MCU must be okay. At this point, I suspected that something went wrong with the compiler options or bootloader. So I decided to ask the Iligo support team for help again and got a reply within a few hours. I decided to try flashing the Iligo Neptune with a Clippy binary compiled with a 48 KB bootloader offset. Luckily, Klipper now finds the MCU, but shows that we still need some mandatory configurations. To continue, I copy the remaining configuration sections from the Citation config example and change the pins with the ones for my printer. Let's move on. We never test a heater before we verify its sensor. We add the full extruder and heater bed sections. The test is simple. Do the temperatures show a plausible room temperature? If you see 0 degrees Celsius, minus 50 degrees Celsius or 400 degrees Celsius, your sensor is not plugged in, wired wrong, or you have the wrong thermistor sensor type. A failure here is critical because if the MCU doesn't know the temperature, the next step could burn out your hot end. Only now, after plugging them in and getting room temperature readings for both sensors, we know they are working. We can test the outputs. We send a low, safe target temperature of 50 degrees Celsius. We watch the graph closely. Success means the temperature climbs steadily and holds. But the most terrifying failure is if the temperature rises uncontrollably past 50 degrees Celsius. That means your heater is stuck on. Hit the emergency stop immediately. You've just saved your printer and your workshop from a fire. We repeat this check for the heated bed. We quickly verify the fans, part cooling and hot end, checking that they spin up with commands and, for the hot end fan, that it turns on automatically when the hot end hits 50 degrees Celsius. Then we move on to the 4-step stepper check for X, Y and Z and the extruder. First, Endstops. Does it read triggered when pressed? Second, motor bus. Does the stepper bus command confirm power is getting through? Third, direction. Activate force movement in the configuration temporarily so you can move the steppers without needing to home first. Don't forget to set it to false again after doing the tests. Then use the force move command to check if the steppers move in the correct direction and the correct distance. Choosing small values for velocity and acceleration gives you enough time to hit the emergency stop button in case anything goes wrong. And fourth, homing. Does it safely stop without grinding? If you pass the 4-step check on all axes, you've survived the hardest part. We wrap up by testing the extruder motor direction and running the final necessary calibrations, PID tune and rotation distance. Then add the missing configuration options for bed size, min and max values for the axis, max temperatures for hot end and heat bed. We've gone from a missing config file and a dark abyss of uncertainty through dangerous hardware detective work to a fully verified and safe custom configuration. So, stick around because after these steps we are finally hitting print. If this framework saved your printer from the scrap heap, then you can support my channel totally free. Drop a comment below and tell me what unsupported printer you resurrected. But if you want me to keep digging up these difficult technical solutions, then please subscribe to make sure this channel keeps growing to continue providing high quality content. Now that your unsupported printer is running Klipper, there's a lot more power to unlock. Whether you need help setting up your final configurations, dialing in your speed and quality, or managing your firmware like a pro, I have more high quality Klipper content ready for you. Check it out! But wait a second, why set up a single color printer when you can immediately print with 12 colors?